Hey guys, well, we've spent the last few weeks talking in detail about what's going on in the nucleus of an atom, and now this is kind of a big transition. We are now going to turn our attention to the electrons, on the outer part of the atom. And one thing we need to learn about before we get into really deep into electronic structure is we need to talk about like the electromagnetic spectrum and wave motion in general. So let's get started. Okay. Okay, come on, computer. All right, so let's talk first, just a very brief introduction about what we mean by waves and wave motion. So when you hear the word wave, what do we usually think about? That's one kind of wave, but actually we're thinking about these kind of waves when we're talking about chemistry and physics. So certainly water is a substance that can exhibit wave-like motion. Here's a big wave here. Here's the aftermath of probably maybe two pebbles that were dropped into this pond at the same time, and you can see the concentric circles of the two wave fronts moving out in all directions. Waves can have different shapes. Here's kind of a nice smooth, like a sine wave. This is more like a couple of different types of sawtooth wave forms. Waves can connect to very different kinds of things. Like here's a fighter jet. I don't know what kind of a fighter plane that is. Looks like maybe an F-15, and it's just breaking the sound barrier, and you can see a shock wave. So that's one kind of a wave, is what they call a shock wave, when an object reaches the speed of sound in the air. Here's other evidence of shock waves in air. This is a bullet caught with very fast action cameras, and you can see the shock wave kind of bowing on either side of the bullet as it's moving. Other kinds of waves, sound waves. You can see that when you're listening to the radio or the television or your stereo, the speaker is basically compressing the air in very specific at specific frequencies, and so you have these areas of compressed air molecules and then relatively uncompressed and alternating, and that's what forms the wavefront when you're listening to sound energy. So just in general, those are some different kinds of waves. But what we are specifically going to talk about is what we call electromagnetic waves. All right. So now let's if you break down the word, you can see just like the fundamental force of electromagnetism, an electromagnetic wave is comprised of two components. There's an electric field component and there's a magnetic field component. And here's one picture that I just pulled off of the web, which I think very nicely exemplifies the shape and the structure of an electromagnetic wave. So what they're showing you is the two components. So in red, the red part of the wave, this is the electric field component of an electromagnetic wave, and the blue is the magnetic field. And you can see, you've got a wavelength here. We'll talk about that in just a minute. There's some anatomy of waveforms that we got to know. But the thing that's kind of interesting, and I'll show you guys more about this in the next couple days, is you might ask yourself, well, what is it that creates electromagnetic waves? What is the origin of an EM wave? And basically, it's just a charged particle that is oscillating back and forth. So whenever charge is accelerated and then decelerated, it generates an EM wave, which is really interesting. And again, it's a composite wave. It has magnetic field vectors and electric field vectors, and they're perpendicular to each other. Okay. All right. So let's just start with the basics. So here is a very standard, garden variety wave. It's basically a sine wave, right, or cosine. And with the dashed line, it simply represents sort of the baseline. All right, so this might be the zero, and when the wave is above the baseline, you could think of that as having positive values, and when it's below, negative values. All right, so let's look at some of the names. So the tops of the waves we just call those peaks, wave peaks. In some books, they'll call it the crest, and then the bottom of the wave is called a trough by most sources and textbooks. Okay. Oh, sorry, little guy, not that kind of trough. So you've got the peak and the trough, and then here's the next peak. And the one very important feature of a wave that we will be dealing with a lot in the next week or so is the wavelength. So the wavelength of a wave, of an EM wave, tells you a lot about the energy and the frequency of the wave. And the wavelength is defined as the distance between two adjacent wave peaks. And I think you can see, because of, this is pretty symmetrical, you could also measure the wavelength between two successive troughs, okay? So it's just the distance between one point, and then as you go down the wave, when you go through one complete cycle, you get to the corresponding place on the next cycle, and that's a wavelength, all right? The symbol, you knew this was coming, right? We have to use goofy symbols for all of these properties. The universally recognized symbol for wavelength is this funny looking thing. It looks like an upside down Y, and this is what we call lambda. So it's from the Greek alphabet, and it's the lowercase lambda. So when we say the word lambda or wavelength, they're kind of synonymous. Now, another feature of the wave is is the distance from the peak to a trough. Okay, so this is a measure of the strength of the wave. How intense is it, and that's given by the amplitude. So if you're given a wave like this, and somebody asks you, for the amplitude, you would simply look at the measurement between the peak and the trough. Now, waves can have all different kinds of wavelengths. So here, I think you can see that the wavelength of this wave is quite a bit smaller than the wavelength for this wave. Okay. You might be thinking, well, what about frequency? I thought I heard that when you talk about waves, you got to talk about frequency. Yes, we're going to talk about that a lot in just a few minutes. But first, we want to get a good feel for what we mean by wavelength. So here, this is kind of a handy little graphic where you can see that they have different names for different sizes of waves. So when you have EM, and we're talking specifically about EM waves from now on, okay, waves that have very long wavelengths are basically in the radio wave range. Okay, so when you're listening to your radio, whether it's FM or AM, the wavelengths of that type of wave tend to be fairly long, like in the meters. Sometimes they're as much as a couple hundred meters. And then when you get a little bit smaller, you get into waves that are about the size of a bee, or even up to about 30 centimeters. Those are microwaves. Then if you get smaller still, infrared. And then if you get really small, here we're in the nanometer range. And there's a very narrow window of wavelength. And this is where kind of our world is, the world of visible light. And you can see that the colors span from red to violet. Okay, Roy G. Biv. Now, if you keep going to smaller wavelengths, then past violet, you get to ultraviolet, and then even smaller still, X-rays, and then the very smallest waves are called gamma rays. And as we'll see a few days down the road, these these EM waves carried the most energy by far. Okay, now here's just kind of a summary of the actual wavelengths that correspond to all these different regions on the EM spectrum. So I'm giving you this as a guide so that if somebody says, hey, I've got an EM wave that's like 100 meters wavelength, you can refer to this if you like, and you can immediately um, you know classify it as a radio wave. Um, also, I just want to let you know that this presentation that you're watching right now, I uploaded it as a PDF. It's on my chemistry materials website, and you'll find it in the electrons and atoms unit. Okay, because now we're in the next unit, and under presentations, there's a link called Introduction to EM Waves, and that's this presentation here. Okay, now just to give you a little bit more of a feel, so I'm borrowing a few images from Carrie Huang's Scale of Universe website. This is the URL, and you guys, we played with this a little bit at the beginning of the year, and I urge you to go back and play with it some more, because this will give you a really good feel for how the size of these various EM waves. So here's AM radio, and you can see the wavelengths are very long. They're getting to be about as long as Central Park, and here's some other things that you can't see very well here, but like here's Hoover Dam, here's the Eiffel Tower. They're very long. Microwaves tend to be about the size of a penny. They can also be as long as about 30 centimeters. Infrared, how big is an infrared wavelength? Well, it's about as big as a skin cell or a mist droplet, and so on. So anyway, I'm not going to go through this in a lot of detail, but you should, I urge you to connect to that website, Scale of Universe, and just kind of get a feel for the scale of these various EM waves. Here's gamma ray. Look how small that is. It's about on the order of a single atom. Okay, here's a screenshot of the daily log for this week, and under today, I've listed. I put up the website. So Scale of Universe. That's the one you want to click on to play with the images of these different waves. All right, now let's just pause here. What I want you to do is pause the video and take your time, take a piece of paper, and I want you to see if you can answer these questions. Okay, and I'm going to check you guys tomorrow. Okay, so I'm assuming now that you paused the video, you went through these questions, and you made a good effort to try to record your responses. Okay, so now let's talk about frequency. Okay, now frequency is denoted by another Greek letter called nu. So the Greek letter nu looks like a kind of a stylized V, right? And that's the symbol we're going to use to represent frequency. Now, what in the heck is frequency? Well, okay, let's say that you're traveling on this wave. First of all, I just want to make a few things clear. As you travel across the wave, all right, what I just illustrated there was one complete cycle. Okay, I start at the peak, I go down the trough, and I arrive at the next peak. Okay, so in order to do that, I had to go through from the peak. I went through the baseline, then I went through the trough, through the baseline again, and finally up to the next peak. That is what we call one cycle of a wave. Frequency it's the number of cycles that you go through per unit time. All right. Now let me just kind of give a couple examples of more familiar types of frequencies. Your pulse rate. Okay, so the number of heartbeats per minute. That's an example of a frequency in a sense. So if your pulse rate is 60, that means that your heart beats 60 times every minute per minute. So and if you consider one heartbeat to be kind of like one cycle, then that's how many cycles per unit time per minute. Another one, those of you who are a little bit familiar with music, in at least in the treble clef when you're reading music, the A that's kind of in the middle of the staff, that note corresponds to 440 vibrations per second. So if you have a tuning fork, if it's an A tuning fork, then they'll have etched on the stem here that'll say 440, and that means that when you kind of tap it on your knee, the metal vibrates back and forth 440 times every second. Okay, now there are units for frequency. Okay, this is the symbol for frequency, but then the actual units are cycles per second. All right, and the units are a little bit strange. It's 1 over s, 1 over second. Okay, and cycles per second is also characterized by the unit hertz. So if something goes through a cycle once per second, the frequency is 1 hertz, and hertz can be abbreviated capital H, lowercase z. Okay, this is named after an actual guy, a scientist, back in the old days. All right, so but I want you to be ready. 1 over s is synonymous with 1 hertz. They mean the same thing, and you need to know that. Okay, now it didn't take long to learn a few things about frequency. So again, I want you to pause the video, and on your paper, I want you to jot down some responses to these 3 questions. Okay, assuming we got that done, so we'll go over these tomorrow. All right, and see how you did. Now, let's get a feel for what the heck frequency is. All right. Well, the first thing you need to know is that electromagnetic waves, they move. When there's an EM source, those electromagnetic waves don't stand still. They're very fast, and in fact, they travel through space at the speed of light. So about as fast as you can get. All right. So let's say here's you, and you're standing still. You're at a fixed point in time, and let's say we're going to take this electromagnetic wave, and we're gonna it's gonna shoot by us. All right, so here we go. Ready? Boom, 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 boom. Okay, so I think you can see that let's try that one more time. Hold on. Yeah. So you can see that the peaks, as the peaks were going by, obviously they were not going by at the speed of light, but the peaks went by you, pretty rapidly. And if you were tapping on a drum, every time a peak went by, it'd be like boom, 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 right? Pretty fast. Now let's take a wave where the wavelength is a little bit longer and see what it would look like. Boom, 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 boom. Okay, so let me do that one more time. So notice the rate, kind of the rhythm of the peaks going by. Now the wave itself is traveling at the same speed as the previous wave, but the frequency with which the peaks, went by your field of vision went by much more slowly. Okay, let's look at that one more time. So here's the EM wave with the smaller wavelength. All right. Okay, hang on. Try that again. Okay. So those peaks went by pretty rapidly. Here's the longer wavelength. Okay. Now, my question for you is, do you see a relationship between the frequency and the wavelength? That is, as we went from a shorter to a longer wavelength, did you notice the difference between how quickly the peaks went by? The first wave, let's say the wavelength was 1 centimeter. Okay. Well, if that was 1 centimeter, then this wave would have had a wavelength of 2.5 centimeters. And so again, looking at the wave with the shorter wavelength go by, boom, 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 and now let's check out the wave with the longer wavelength. Boom, 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 boom. See, the frequency is slower. All right, so that's where we will begin tomorrow. We'll start exploring the actual mathematical relationship between wavelength and frequency. But that's enough for today. Okay, thanks guys. See you tomorrow.